Okay, let's just dive right into this. We're talking about the very foundation of our digital lives and a looming threat that could completely shatter it. Today, we're going to explore the future of cybersecurity. I want you to really, really think about that for a second. Every single password, every secure transaction, every private message you've ever sent. Just poof, wide open. It sounds like something out of a sci-fi movie, but it's a future we're actually racing to prevent. Right now, that foundation feels pretty solid, doesn't it? Encryption is like this invisible armor that protects all of our data. It's the whole reason you can do online banking, send a private email, or trust that super sensitive government communications stay secret. But that armor has a potential weakness. And that weakness, well, it has a name: the quantum threat. And look, this isn't just some small crack in the armor. We're talking about a fundamentally new kind of force that our current defenses were just never, ever designed to handle. So here's the deal. Today's encryption, it's all built on math problems that are so ridiculously hard that our best supercomputers would literally need thousands of years to solve them. But a quantum computer, it just thinks differently. It uses this special trick called Shor's algorithm, which is kind of like a mathematical shortcut. And with that, it can pick those locks with ease, basically making our current security totally obsolete. So naturally, the race is on to build new locks. But the first attempts have had some pretty major drawbacks. You've got true quantum cryptography, which is super powerful, but it requires completely new, crazy, expensive hardware that's just not practical for you and me. And then other post-quantum software ideas, well, they often have their own issues, like massive key sizes that just slow everything down to a crawl. And this is where the source material we're digging into proposes a totally different path. Instead of just trying to make a stronger version of the same old lock, what if we built a completely new kind of shield, one that's actually designed for this new era? The source material introduces this one system. It's called the QSP cryptographic protocol. And you want to know its biggest selling point? It's designed to give us that top-tier, quantum-level security, but run on the classical hardware we all have right now. Yep, no expensive new infrastructure needed. This table really lays out the key differences. So you see, while traditional crypto is vulnerable and a lot of the post-quantum fixes are, well, they're clunky, this protocol aims for a totally different approach. Check out that bottom row. Instead of static keys or these gigantic keys, it uses something called entropy, which is basically just randomness, to stay super efficient on the systems we already use. So how in the world does it actually work? This is where things get really fascinating. The whole system kind of moves away from purely mathematical problems and starts to draw its strength from the physical world around us. I absolutely love this analogy from the source material because it just makes the concept so crystal clear. This isn't some static safe that a new tool can eventually crack open. No, it's a dynamic, adapted defense that is constantly changing. It makes it a completely unpredictable and moving target. Now, the core idea behind this whole shape-shifting vault is a principle called space-time occupancy, or STO for short. And in simple terms, it just means using the real physical world, factors like time and the complete unpredictable randomness of our environment, to build the layers of our digital security. This entire approach is built on 3 key innovations. First, instead of static keys, it uses entropy to generate dynamic keys from all sorts of unpredictable sources. Second, it chops up data into these time-based segments so an attacker can't just go after one big file. And third, and this is wild, it can even use environmental sensors, like the background heat or sound in a room, to add even more layers of randomness and security. And here's a very specific number to make this tangible. The protocol aims for what it calls a phase coherence of 99.63%. You can think of this as the system's heartbeat. It's this constant measure of security integrity. So if an attacker tries to mess with anything, that number drops, and the system knows instantly that it's under attack and can react. So, you see, this isn't just some theoretical exercise. The implications of this kind of technology are absolutely massive. Let's take a look at what it really means to future-proof our digital world. I mean, the applications cover pretty much every critical part of our society. We're talking about the global financial system, military communications, the cloud, the crypto in our digital wallets, and even down to the billions of tiny Internet of Things devices that help run our world. And make no mistake, this is a huge shift. The sources we looked at project that the industry for these quantum-safe solutions could be worth over $500 billion by 2028.
A number like that just shows you how seriously the world is taking this threat and the incredible scale of the transformation that's coming.
So, as we start to wrap up, it's pretty clear we're standing right on the edge of a new frontier in cybersecurity. The old walls we've relied on, they're about to become obsolete. At the end of the day, this has always been true, hasn't it? Cybersecurity is a constant cat and mouse game. For every new type of lock someone invents, someone else is already working on a new type of key. This quantum leap is just the next major chapter in that race. And that really leaves us with the final question. As quantum computing evolves from just a theory into a reality, are our new defenses, like the ones we've explored today, evolving fast enough? Are the locks we're building right now truly ready for the keys of tomorrow?